Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual firmament of the 20th century, certain scientific papers function less as containers of data and more as conceptual fulcrums, shifting the very ground upon which a discipline stands. Edward Norton Lorenz 1968 paper titled Climatic Change as a Problem in Nonlinear Dynamics, published in the Proceedings of the National Academy of Sciences, represents precisely such a contribution, while his earlier 1963 work on deterministic non-periodic flow is celebrated for introducing the world to chaotic dynamics. This later, shorter, and more condensed paper offers a profound and specific application of this worldview to the grand challenge of climate. It is a work of immense theoretical elegance and audacious implication, proposing a fundamental reconceptualization of what climate is and how it changes. This essay undertakes a rigorous, section-by-section evaluation of the internal claims, logical architecture, and specific arguments presented within this landmark paper. It will explore how Lorenz, with a minimalist mathematical toolkit, constructed a compelling case for the existence of intrinsic, long-term climatic variability, a concept he crystallized with the term almost intransitivity. The analysis will proceed sequentially through the paper's dense arguments, evaluating the coherence of its logic, the purpose of its methodology, and the revolutionary nature of its conclusions about the Earth's climate system. Section 1 of Foundational Taxonomy of Dynamic Systems. The paper commences by establishing a crucial conceptual framework dividing dynamical systems into three distinct categories based on their long-term statistical behavior. Lorenz begins with the familiar concepts of transitive and intransitive systems. He defines a transitive system as one where the time averages of its properties, calculated over a sufficiently long interval, are independent of the initial conditions. This is the classical assumption underpinning many statistical, mechanical, and climatic theories that a system, given enough time, will explore all of its accessible states, rendering its long-term climate a unique and stable property. He then presents the contrasting case of an intransitive system. Here, the phase space is partitioned into two or more regions, and a trajectory that begins in one region remains there forever. Consequently, such a system possesses multiple distinct sets of long-term statistical properties, or multiple possible climates, with the realized climate depending entirely on the system's starting point. The brilliance of this introductory framing lies in its intellectual positioning. Lorenz leverages established mathematical language to create a clear classificatory scheme for dynamics, preparing the reader for the introduction of a novel, intermediate category. He presents these definitions with an air of settled science, a stable platform from which he will launch his primary inquiry. The evaluation of this opening section reveals it as a masterstroke of rhetoric and scientific exposition. It furnishes the essential vocabulary for the remainder of the paper and frames the central question implicitly into which of these categories, or perhaps the new one, does the Earth's climate fall? This section claims that this taxonomy is a valid and useful lens for understanding climate, a claim whose power is fully vindicated by the analysis that for Section 2 the architecture of an 8-variable atmospheric analogue following the conceptual groundwork, Lorenz introduces the specific mathematical tool for his investigation, a highly simplified model of atmospheric circulation. The model is presented as a system of 8 coupled ordinary differential equations, representing a severe truncation of a more complex spectral model developed by Barry Saltzman. Lorenz is explicit about the model's idealized nature, stating its purpose is to capture general principles rather than to simulate the real atmosphere with fidelity. The system of equations is presented directly. The rate of change of a primary variable, designated x1, which represents the intensity of the globally average westerly wind current, is shown to depend on the squares of two other variables, x2 and x3, representing cosine and sine phases of larger scale atmospheric waves. This equation also includes a linear damping term, -1/4 times x sub 1, and a constant thermal forcing term, represented by the letter F. The subsequent 7 equations describe the rates of change for the other wave component variables, forming a closed, nonlinear system. The evaluation of this section must focus on the legitimacy of using such a toy model to make profound claims about climate. The internal logic is impeccable. Each term has a physical analogue, albeit a simplified one. The quadratic terms represent the nonlinear transfer of energy between the mean flow and the eddies, the central engine of atmospheric dynamics. The forcing term F represents the steady solar energy input that drives the entire system. The claim here is methodological that a minimal system, strict of geographical detail and countless physical processes, can still retain the essential nonlinear character of the climate and serve as a valid tool for exploring its fundamental dynamic possibilities. This is a powerful assertion about the practice of theoretical science, suggesting that insight arises from simplification and the isolation of core mechanisms. The model is a theoretical artifact designed for conceptual exploration, and its validity rests entirely on what it reveals in the subsequent analysis. Section 3: A numerical experiment in long-term climatic behavior. This section details the results of a numerical integration of the 8-variable system. This is the empirical heart of the paper, where the abstract model is set in motion to produce a tangible result. Lorenz specifies the parameters used in the experiment. The forcing term F is set to a value of 8, and the initial conditions for the 8 variables are chosen. He then describes the outcome of integrating the equations over an exceptionally long period, equivalent to many thousands of simulated days. The primary claim emerging from this experiment is the observation of a remarkable and unexpected behavior in the solution. For the first 500 simulated days, the variable x sub 1, representing the westerly winds, oscillates with a fairly regular period around a mean value of approximately 2. This represents a stable, well-defined climate state. Following this extended period of relative regularity, the system's behavior changes dramatically. The oscillations of x sub 1 become chaotic and aperiodic, and its mean value begins a slow, meandering drift downward. After about 300 more simulated days, the system settles into a completely different statistical regime. In this new state, x sub 1 oscillates chaotically around a negative mean value of approximately -1.5. This second climate persists for another 500 days before the system transitions back, again after a period of chaotic wandering, to the original state centered around a positive mean. The evaluation of this section centers on the power of this single numerical result. Lorenz presents it as a stark piece of evidence. The claim is that this single time series demonstrates that a deterministic system with constant external forcing can spontaneously generate its own dramatic, long-term climatic shifts. The graphical representation of this result, described in the paper, would have been a startling visual for his contemporaries, a clear depiction of a system vacillating between two very different, long-lasting climatic states without any change in external conditions. The methodology is straightforward numerical integration, but its outcome is a profound challenge to the prevailing view of climate as a unique response to external forcings. Section 4: The conceptual leap to almost intransitivity. Here, Lorenz synthesizes the results of his numerical experiment to formulate the paper's central theoretical contribution, a concept of an almost intransitive system. He uses the behavior of his model to argue for the existence of a third class of dynamical system, one that sits between the fully transitive and the strictly intransitive. He defines an almost intransitive system as one for which the long-term statistics are stable when computed over very long, yet finite, intervals, but where different initial conditions can lead the system to different, long-lasting statistical regimes. The key distinction from a truly intransitive system is that in an almost intransitive system, transitions between these regimes are possible, although they may be rare and occur at irregular intervals. In such a system, the climate, defined as a set of time-averaged statistics, is dependent upon the time interval over which one is averaging a state of affairs that would be anathema to a classical transitive system. The evaluation of this claim reveals its deep philosophical implications for climatology. Lorenz is effectively arguing that climate may lack a single, permanent statistical equilibrium. Instead, the climate we observe could be a temporary resident of one of several possible states, with the potential for an unforced, internally generated shift to another state at some unknown future time. This claim recasts the very definition of climate from a static boundary condition to a dynamic, path-dependent process. He uses his model's behavior as the type specimen for this new category. The long periods spent oscillating around positive and negative mean values for the distinct climates, and the chaotic transitions between them, are the proof that the system is not truly intransitive. The claim is elegant and logically derived from the preceding numerical evidence. It provides a name and a formal definition for a behavior that, once described, seems almost necessary to explain the complexities of Earth's own climatic. Section 5, reinterpreting Earth's climatic past in the paper's penultimate section. Lorenz extends his theoretical finding to the real-world problem of the Pleistocene ice ages. This is where the abstract model makes a direct and ambitious connection to a major question in Earth science. He proposes that the phenomenon of almost intransitivity offers a compelling alternative or supplementary explanation for the observed oscillations between glacial and interglacial periods. The prevailing theories of his time, such as the Milankovitch cycles, relied upon external, periodic forcing from variations in Earth's orbit to explain these massive climatic shifts. Lorenz's claim is that the climate system itself may possess the internal dynamics necessary to generate such cycles. The two distinct statistical regimes observed in his simple model, one with strong westerly flow and one with weaker, even reversed flow, are presented as analogues for interglacial and glacial climates. The spontaneous, internally driven flipping between these states in the model is offered as a mechanism that could produce ice age cycles without any required change in solar output or orbital configuration. Critically evaluating this claim, one must acknowledge its audacity and its conceptual power. It does not dismiss the role of external forcing but asserts that the internal, nonlinear dynamics of the climate system are a powerful agent of change in their own right. This fundamentally alters the scientific search for causes. Instead of looking solely for an external trigger for every climatic shift, scientists must also consider the possibility that the system is simply evolving according to its own complex, almost intransitive rules. The claim reframes the ice age problem from a simple cause-and-effect relationship to a problem in the stability and internal variability of a complex nonlinear system. This was a radical perspective that opened up entirely new avenues of research in paleoclimatology. Section 6, concluding reflections on climatic determinism and predictability. The paper's conclusion is brief but potent, summarizing the profound implications of its findings. Lorenz reiterates that the central result is the demonstration that a system with constant external parameters can exhibit behavior that appears, for all practical purposes, to be a long-term climatic shift. The core claim here is a final meditation on the nature of climate itself. If the climate is an almost intransitive system, then it possesses a form of intrinsic indeterminacy. The specific climate of a given epoch could be, in some sense, a matter of historical accident, dependent on the system's trajectory through its vast phase space. A further implication, which connects this work back to his 1963 paper, is that predicting which climatic regime will be occupied and for how long is an exceptionally difficult, perhaps impossible, task. The transitions are chaotic and lack a clear, predictable period. The evaluation of this concluding section shows it to be a masterclass in scientific understatement. Without grand pronouncements, Lorenz lays out a new worldview. He suggests that the very question, what is the climate, may have multiple correct answers depending on the timescale of interest. The final claim is that climatic change must be understood as a problem in nonlinear dynamics, a field where intrinsic variability and sensitive dependence on initial conditions are the governing principles. This assertion permanently altered the foundation of climate science, moving it away from a search for simple equilibrium states and toward the study of complex, evolving, and fundamentally unpredictable systems. In conclusion, Edward Lorenz, 1968 paper, Climatic Change as a Problem in Nonlinear Dynamics, stands as a monument of theoretical science. The essay's exhaustive evaluation of its internal claims, from the initial framing of systemic behavior to the final, profound implications for paleoclimatology, demonstrates its remarkable logical coherence and intellectual force. Through a section-by-section analysis, we see how Lorenz built his case with meticulous care. He began by establishing a necessary vocabulary with the concepts of transitivity and intransitivity. He then constructed a deliberately simplified mathematical model, arguing for its validity as a conceptual tool for exploring fundamental dynamics. From this model, he produced a single, compelling numerical result, a time series demonstrating spontaneous shifts between two distinct, long-lasting statistical regimes. This evidence became the bedrock for his central theoretical innovation, the definition of the almost intransitive system, a new category of behavior that recasts our understanding of stability and change. Finally, he audaciously applied this abstract concept to the concrete problem of the Ice Ages, proposing that the climate system contains within itself the seeds of its own transformation. The work's enduring significance lies in this elegant and powerful demonstration that immense, epoch-spanning climatic change can arise from the internal, non-linear dynamics of the atmosphere-ocean system alone, independent of external drivers. It is a work that teaches a timeless lesson that in the study of complex systems, the most profound insights often come from the simplest models that dare to ask the most fundamental questions. The paper functions as a permanent intellectual charter for the field of modern climate dynamics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.